Have you ever wished you could just control sound? I don't just mean blocking it. I mean bending it, focusing it, maybe even making something totally invisible to sound. Well, today we're diving into a class of materials that can do exactly that. They honestly look like they're from the future, and they let us play with sound in ways that seem to, well, break the laws of physics.
You know the feeling, that deep, low rumble from a highway or a train passing by. It's the kind of noise you don't just hear with your ears. You actually feel it vibrating through the walls. That's low-frequency noise, and it is notoriously, incredibly hard to stop. So why is that? It really all boils down to a fundamental rule of physics.
And here's that rule. It's called the mass law of acoustics. And simply put, it says that if you want to stop sound, you need mass, lots of it. And for that deep, low-frequency sound, you need your barrier to be even thicker and heavier. It's why we use gigantic concrete walls for serious soundproofing. But let's be real, you're not going to build a 10-foot thick concrete wall around your bedroom. It's just not practical. And this chart here shows you the problem perfectly. The usual stuff, like the foam or mineral wool you'd find in walls, they're actually pretty good at soaking up high-frequency sounds, all the hisses and whirs. But look what happens at the low end. Their performance just plummets. They're basically useless unless you make them ridiculously thick.
Okay, this is where it gets really, really cool. What if we could just sidestep that mass law completely? What if we could engineer a material that's thin and lightweight, but could still stop that deep rumble dead in its tracks?
We'll enter acoustic metamaterials, or AMMs for short. These are not materials you find in nature. They're totally man-made, and their magic isn't in what they're made of. It's not about the chemistry. It's all about their geometry. Their incredible ability to mess with sound comes from their internal architecture, these super intricate, repeating structures that are smaller than the sound waves they're designed to control. And researchers G. Eiden and S.E. San put it perfectly. It's this periodic arrangement of subcomponents that unlocks acoustic powers you just can't get with any normal material. It's all about the shape. So how in the world do these bizarre-looking structures actually rewrite the rules of sound? To get our heads around that, we need to look at how they create physical properties that, frankly, shouldn't exist in nature. All right, first up is this absolutely mind-bending idea called negative effective mass. So imagine you push a shopping cart. You expect it to roll away, right? Well, what if it accelerated back at you? It's totally bizarre, but by using tiny internal resonating parts, engineers can make a material react to the push of a sound wave by, in effect, moving against it. And that creates one heck of an effective sound barrier.
Okay, next up is negative bulk modulus. Normally, if you squeeze something from all sides, it gets smaller. Makes sense. But these materials do the exact opposite. They actually expand when you compress them. This is done with arrays of tiny resonant cavities, kind of like millions of tiny soda bottles. When a sound wave comes along and tries to squeeze them, the air inside resonates and pushes back, forcing the whole structure to expand against the wave. It's another weird but powerful tool for controlling sound. And finally, there's this really clever trick called space coiling. The best way to think about it is like folding up a super long winding hallway and cramming it into a tiny little box. A sound wave goes in, and it's forced to travel this crazy, long, maze-like path to get out the other side. This creates a massive time delay in a really compact space, giving engineers yet another way to precisely control sound waves. So this table kind of puts it all together. You can see how these wild ideas become real structures. If you want that negative mass we talked about, you can use things like tiny weights on springs or special membranes. For that negative modulus, you use those Helmholtz resonators, the tiny bottle-like things. And for extreme sound bending, those space coiling labyrinths give you something called a high refractive index. Each design is a different tool in the toolbox for total sound control. Okay, so we can build materials with these impossible, unnatural properties. What do we actually do with them? Well, this is where we go from the really cool science to stuff that sounds like it's straight out of science fiction. So first things first, we can finally solve that problem we started with. We can design thin, lightweight panels that are incredibly effective at blocking that stubborn low-frequency noise. We can just completely shatter that old mass law.
And the difference is just And the difference is just dramatic. Look at this chart. Down in those tough low frequencies, a traditional wall is barely doing anything. But a metamaterial panel, which can be way thinner and lighter, is blocking significantly more sound. The takeaway here is huge. You get way better performance with a fraction of the weight and space. And it gets even crazier. Using these same principles, we can literally build acoustic cloaks. We're talking about shells that you can put around an object that are designed to guide sound waves perfectly around it, as if it wasn't even there. For any microphone or listener on the outside, the object inside is acoustically invisible.
We can also create something called an acoustic superlens. See, in physics, there's a hard rule called the diffraction limit. It basically says there's a limit to how small of a spot you can focus a wave to. Well, the acoustic metamaterials can just smash right through that limit.
Now, this is a total game changer. A superlens can focus sound to a spot that is just 1/15th the size of its own wavelength. Just think about what that means for something like a medical ultrasound. It means doctors could potentially see details inside the human body with a resolution they have never, ever had before. This could completely revolutionize how we diagnose diseases. So, this technology is clearly incredible. But how do we actually make these things? And if they're so great, what's stopping them from being everywhere already? Let's take a look at the journey from the lab out into the real world.
Right, this is the key question. How do you manufacture materials that have these insanely complex, precisely engineered structures inside of them, often on a microscopic scale? Well, the answer lies in a technology that's really grown up right alongside metamaterials science.
The answer is high-precision additive manufacturing, or as we all know it, 3D printing. As you can see from this list, it's not just one thing. It's a whole suite of different technologies, from lasers to material jetting, that let scientists build these complicated designs layer by tiny layer, giving them the insane accuracy they need to make these acoustic properties a reality.
But we're not quite there yet. There are still some big hurdles. On one hand, the promise is crystal clear. Lightweight materials with tunable performance and just superior sound control. But on the other hand, a lot of today's designs only work for a narrow range of sounds. They can be really expensive to make, and figuring out how to scale up production from a single lab prototype to, a million of them is a huge challenge that researchers are tackling right now.
We are seriously on the edge of a revolution in how we deal with sound. So as scientists and engineers keep chipping away at these problems, what will that world look like and sound like? Just imagine it. Perfectly silent apartments right next to an airport. Medical scanners that can spot diseases at the earliest possible stage. Concert halls with absolutely flawless acoustics for every single person in the room. A world with total sound control isn't just sci-fi anymore. It's being built right now in labs all over the world, one intricate layer at a time.